We're going to go over the basics for finding a differential equation and linear approximation in number 1. So number 1 gives you the differential equation dy over dx is equal to y minus 2 over x squared. And it wants you to find a particular solution to the differential equation at the point 1, 3. This should be reviewed from Calculus AB, so I'm only going to briefly go over the process. We're going to do separation of variables and then integrate both sides. As you can see here, I moved y minus 2 to the left side, so it becomes 1 over y minus 2. And then I multiply both sides by dx. Next, you're going to integrate both sides. The antiderivative for 1 over y minus 2 is going to be the natural log of the absolute value of y minus 2. The antiderivative for x to the negative 2 is negative 1 over x. Technically, both sides should have a plus c, but we can subtract the 1 from the left to simplify down to only 1c to make our work later a little easier. If the question had been asking for the general solution to the differential equation, you could simply leave the c in the expression and start simplifying it. But because the question wants our particular solution to a particular point, you would have to find what c is. You can generally find c whenever you want during the simplification process and simply carry it down to your final answer. Here, I'm going to find the c immediately after integration. To find c, you're simply going to plug in x and y from your initial condition. In this case, x is 1 and y is 3. This expression simplifies to c equals 1. After you have found c, plug it back into the original equation. So now we have the natural log of the absolute value of y minus 2 is equal to negative 1 over x plus 1. The rest is all algebraic simplification. You're going to raise both sides to the power, eliminate the absolute value sign by putting plus or minus, and then move any constants to the right, so the left side of the expression is only y. After that, we get y is equal to plus or minus e to the negative 1 over x plus 1, all plus 2. But the final particular solution should not contain a plus or minus sign in it.
This is a common mistake.
In this case, we're going to plug in the initial condition 1, 3 into the expression again and determine the sign. Plugging in the initial condition gives us that 3 is equal to plus or minus e to the negative 1 over 1 plus 1 all plus 2. This expression holds true when the sign is positive. So in the final answer, we're only going to write y is equal to positive e to the negative 1 over x plus 1 all plus 2. Part B asks for the equation of the tangent line at 1, 3. Finding the equation requires a point and a slope. The point is already given, so we only have to find what the slope is. To find the slope, we can plug in the point into the differential equation. In this case, we get 3 minus 2 over 1 squared, which simplifies to 1. Plugging in slope is equal to 1 and then the point into the point-slope formula, we get that the tangent line equation is y minus 3 is equal to x minus
1. Part 3 asks you to
find the y value f of 2 using the tangent line equation found in part B. Simply plug in x is equal to 2 into the equation and you would get y is equal to 4.
Okay, now we're going to practice Euler method with this equation. Y prime equals 6x plus 3y, y of 0 equals 0. In 4 steps, approximate f of 2. Now, the first step to do this is we need to find the slope of the first form. So we need to plug in 0, 0 into the y prime equation. So then when we plug it in, we're just going to get y prime equals 0. Now we need to find the point slope form of the first step. Since we need to find it in 4 steps, we're going to divide 2 by 4. So when we divide that by 4, we get 0.5. So that's what our first x value is going to be. So now we plug it in, y minus 0 equals 0 times x minus 0, which is the point slope form. And then we add in the x value that we need, 0.5. So then it becomes y minus 0 equals 0 times 0.5 minus 0, which ultimately equals 0. Now we're going to do the second step. Now with the second step, we have our 0.5, 0 coordinate that we got from the last one. So we're going to plug in to find a new slope, because every single time we're going to need to find a new slope for the new point slope equation.
Not finding a new slope is a common mistake.
So when we plug it in, y prime equals 6 times 0.5 plus 0, which ultimately is going to equal 3. So now you found the slope equals 3. Then you find the point slope equation for the second one. So you just plug in the x, y value that you got from the first step and plug it into the point slope form. You get y minus 0 equals 3 times x minus 0.5. When you plug in the coordinates 1, because that's your next step, y equals 3 times 0.5, and ultimately y equals 1.5. Now, your next coordinate will be 1, 1.5. Now we're on to the third step. Again, we need to find the next slope. So, we'll plug 1, 1.5 into the equation again. So, 6 times 1 plus 3 times 1.5 is going to equal 10.5. That's our new slope. Then we plug it back into our new point slope form, which is y minus 1.5 equals 10.5 times x minus 1. Now, our next step is going to be another 0.5 above 1.5. So, now we have y equals 10.5 times 0.5 plus 1.5. And now our y is equal to 6.75. Now we are on our final step. Now, since we have 1.5 and 6.5, you guys know what to do. We need to plug it in and find our new y prime slope. Now, we plug in 6 times 1.5 plus 3 times 6.75, which is going to ultimately equal 29.25 as our new slope. Now, I'll plug it back into our fourth and final point slope form equation. Y minus 6.75 equals 29.25 times x minus 1.5. Now, once we plug in our
2.
we're going to get y equals 29.25 times 0.5 plus 6.5
7.
to finally get y equals 21.375. Now, this is going to be f of 2 is approximately equal 21.375.
Now let's look at our logistics growth problem. A rainforest consisting 5 million animals. The current population is at 3 million. 1 year ago, the population was at 1.5 million. First, let's find P of t. Recall that P of t is equal to k over 1 plus a times e to the negative rt. A is equal to the carrying capacity minus the initial population over the initial population. So we plug in 5 million minus 1.5 million over 1.5 million. Notice how we are using the population 1 year ago as our initial population. So the current population at 3 million is at t equals 1. So then to solve for r, we plug everything in. Then we isolate r by cross-multiplying and subtracting 3 million from both sides. After dividing by 7 million, we get e to the negative r is equal to 2 over 7. Taking the ln of both sides, we get negative r is equal to ln of 2 over 7, and r is equal to the negative ln of 2 over 7. So now plugging everything in, we get P of t equals 5 million over 1 plus 7 over 3 times e to the ln of 2 over 7 times t. One common mistake is putting a negative sign in front of the ln. However, you have to remember that e is being raised to the negative rt power. So if r is equal to negative ln of 2 over 7, then negative r is equal to positive ln of 2 over 7. Moving on to part b, find p prime of t. Recall that the formula for p prime of t is r times p times 1 minus p over k, where k is again the carrying capacity, and r is the rate that we just found. So we can plug in negative ln of 2 over 7 for r and 5 million as the carrying capacity. And that's all we have to do for part B. For part C, we want to find the population in 2 years. This means that t is equal to 3 because the current population is at t equals 1. The tricky part for part C is to figure out what the problem is asking for and setting t equal to the right number. Once you figure that out, you can easily plug everything in and get the population in 2 years will be approximately 4.7 million.
Part D asks, at what time did or will the population grow the fastest? The population grows the fastest when it reaches half of carrying capacity, which is K divided by 2, and would equal 2.5 million. To find what time the population reaches 2.5 million, we take the equation we found in part A for population and set it to 2.5 million. From there on, we just simplify to isolate t, which is time. In the first step, I multiply the denominator to 2.5 million and then divided 2.5 million from that side to get 1 plus 7/3 times e to the ln of 2/7 times t, which equals 2. Then subtract 1, and then multiply both sides by 3/7. Remove the e by taking the ln of 3/7. Then divide both sides by ln of 2/7. Using a calculator, we would find that t equals 0.6763 years, which is about 8 months. But because our initial population was set at 1 year ago, so 1 year ago would be our 0 in time, 8 months would have been reached 4 months ago. So our answer would be 4 months ago. Part E asks, how long will it take for the population to increase to 4 million? Similarly to Part D, we will use the equation found in Part A for population. Set the equation to 4 million. From there on, simplify. Multiply the denominator, and then divide both sides by 4 million. Subtract 1 from both sides. Multiply both sides by 3/7. Take the ln to get rid of the e. Then divide both sides by ln of 2/7. Then you'll get that t equals 1.7829 years. Since we are currently at t equals 1, it would take 1.7829 minus 1, which equals 0.7829 years from now. Part F asks, what are the 4 important limits? The 4 important limits are limit of p of t as t approaches negative infinity, limit of p of t as t approaches positive infinity, limit of the first derivative of p of t as t approaches negative infinity, and the limit of the first derivative of p of t as t approaches positive infinity. Below I have graphed the logistic curve of p of t. Looking at the graph, we can see that the first limit would equal 0, while the second limit would equal k, which is 5 million, and the third limit would equal 0, and the fourth limit would also equal 0 as the graph levels off at the top. A common mistake is not factoring the first derivative of p of t properly. If you try to determine k, carrying capacity, from the first derivative of p of t, make sure your formatting is right. It should be r times p times 1 minus p over k. For example, if our equation dp over dt equals 0.1 times p times 2 minus p over 500, and we wanted to find the carrying capacity, we would have to first factor out 2, so that the equation equals 0.2p times 1 minus p over 1000. Then, from that equation, we'd be able to find that the carrying capacity is 1000, not 500.